Discuss predicates and quantifiers. Propositional logic can be adequately expressed the meaning of all statement in mathematics and in natural language. Okay, so for example, suppose that uh, every computer connected to the school network is functioning properly. No rules of a propositional logic allows us to conclude the truth of the statement. Let's say Math 3 is functioning properly, where Math 3 is one of the computers connected to the school network. Likewise, we cannot use the rules of propositional logic to conclude from the statement, let's say CS2 is under attack by an intruder, where CS2 is a computer on a school network, to conclude the truth of there is a computer on the school network that is under attack by an intruder. So in this discussion, we will introduce a more powerful type of logic called predicate logic. Okay, we will see how predicate logic can be used to express the meaning of a wide range of statements in mathematics and in computer science in ways that permits us to reason and explore relationship between objects. To understand predicate language or predicate logic rather, we first need to introduce the concept of predicate. Okay, afterwards, we will introduce the notion of quantifiers, which enables us to reason with statements that assert that a certain property holds for all objects of a certain type, with the statement that asserts the existence of an object with a particular property. So let's start with the uh, predicates. So the statement involving the variables such as we have x greater than 3, we have x equals y plus 3, x plus y equals z, and computer x is under attack by an intruder, and computer x is functioning properly are often found in the mathematics assertion and in system specifications. These statements are neither true or false when the values of the variables are not specified. In this discussion, we will discuss the ways the propositions can be produced from such statements. Okay, the statements x is greater than 3 has two parts. The first part, the variable x, is the subject of the statement. The second part, which is the predicate, is greater than 3, refers to a property that the subject of the statement can have. We can denote the statement x is greater than 3 by p of x, where p denotes the predicate is p denotes the predicate is greater than 3, and x is the variable. The statement p of x is also said to be the value of the propositional function p at x. Once a value has been assigned to the variable, the statement p of x becomes a proposition and has a truth value. So let's have these examples. So for example, let p of x denote the statement x is greater than 3. What are the truth values of p of 4 and p of x? So in this case, we have the values now of our x. So for the solution, okay, we obtain the statement p of 4 by setting x equals 4 in this statement, x greater than 3. Hence, p of 4, which is the statement 4 greater than 3, is true. However, p of 2, which is the statement 2 greater than 3, is false. Okay. So we have here another example. Let a of x denote the statement computer x is under attack by an intruder. Suppose that one of the computers on campus, only CS2 and MATH1, are currently under attack by intruders. What are the truth values of A of CS1 and A CS2 and A Math 1? Okay, so in this case, we could have we obtain the statement A C of A C S1 by setting X equals CS1. In the statement, computer X is under attack by an intruder. Because CS1 is not on the list of the computer currently under attack, we conclude that A of CS1 is false. Similarly, because CS2 and MATH1 are on the list of the computer under attack, we know that CS2 and A of MATH1 are true. So we can also have the statements that involves more than one variable. For instance, consider the statement x equals y plus 3. Okay, we can denote this statement by q of the um, ordered pair xy, where x and y are the variables and q is the predicate. When values are assigned to the variables x and y, the statement q of the ordered pair xy has a truth value. Okay, so let's have an example. So let q of the ordered pair xy denote the statement x equals y plus 3. What is the truth values of the proposition q of 1, 2 and q of 3, 0? So in this case, we have this solution. So to obtain the q of 1, 2, set x equals 1 and y equals 2 in the statement q of x, y. Hence, q of 1, 2 is the statement 1 equals 2 plus 3, which is false. The statement q of 3, 0 is the proposition 3 equals 0 plus 3, which is true. Okay. So very explainable. Okay, so let's have preconditions and postconditions. Okay, predicates are also used to establish the correctness of computer programs. That is to show the computer programs always produce a desired output when given a valid input. So the statement that describes a valid input are known as preconditions, and the conditions that the output should satisfy when the program has run are known as postcondition. Okay, so let's have another statement that is very essential in discussing these discrete mathematics. Let's have the universal quantifiers. Okay, when we are talking about quantifiers, uh, when the variable in a propositional function are assigned values, the resulting statement becomes a proposition with a certain truth value. However, there is another important way called quantification to create a proposition from a propositional function. Quantification expresses the extent to which a predicate is true over a range of elements. Okay, so in English, the word all, some, many, none, and few are used in quantification. Okay, we will focus in two types of quantification where uh, where we call it universal quantification, which tells us that the predicate is true for every element under the consideration, and existential quantification, which tells us that there is one or more element under consideration for which the predicate is true. So the area of logic that deals with predicates and quantifiers is called predicate calculus. So let's start with universal quantifiers. Okay, many mathematical statements assert rather that a property is true for all values of the variable in a particular domain, which is called domain of discourse or the universe of discourse, often just referred to as the domain. Such a statement is expressed using universal quantification. The universal quantification of p of x for a particular domain is the proposition that asserts that p of x is true for all values of x in this domain. Note that the domain specifies the possible values of the variable x, meaning of the universal quantification of p of x changes when we change the domain. So the domain must always be specified when a universal quantifier is used. Without it, the universal quantification of the statement is not defined. So let's have, okay, this definition. So the universal quantification of p of x is a statement p of x for all values of x in the domain. The notion, this symbol, okay, this symbol denotes the universal quantification of p of x. Here, this symbol is called universal quantifier. We read this one as for all x p of x, or for every x p of x. The element of which p of x is false is called counterexample of the for all, as we call, for all x p of x. Okay. So the meaning of the universal quantifier, okay, can be illustrated in the universal quantifier in the following examples. Okay. Okay, so let's have this one. Okay, this statement. The statement, this statement for all x p of x, when true, p of x is true for every x. When false, there is an x for which p of x is false. Okay, so for this symbol, okay, when true, there is an x for which p of x is true. And when false, p of x is false for every x. Okay, so let's have an example. Let p of x is a statement x plus 1 greater than x. What is the truth value of the quantification for all xp of x where the domain consists of all real numbers? So in this case, because p of x is true for all real numbers x, the quantification for all x p of x is true. Okay. So generally, an explicit assumption is made that all domains of discourse for quantifiers are non-empty. Note that if the domain is empty, then for all x, p of x is true for any propositional function p of x, because there is no element x in the domain for which p of x is false. Besides, for all and for every, universal quantification can be expressed in many other ways, including all of, for each, we have given any, for arbitrary, for each, and for any. Okay, so it is best to avoid using for any x because it is often ambiguous as to whether any means every or some. So that's the reason why, as much as possible, we are not going to use for any x. In some cases, any is unambiguous, such as when it is used in negatives. For example, there is not any reason to avoid studying. So that is also the any there is very clear. Okay, it's not ambiguous. um, the statement for all x, p of x is false, where p of x is a propositional function if and only if the p of x is not always true when x is the domain. One way to show that p of x is not always true when x is the domain, when x in the domain rather, is to find a counterexample to the statement for all x p of x. Note that the single counterexample is uh, is all we need to establish that for all x p of x is false. So let's have this example. Um, what is the truth value of for all x p of x, where p is the statement x squared less than 10, and the domain consists of the positive integers not exceeding 4. Okay, so okay, for the solution, this statement for all x p of x is the same as the conjunction p of 1 and p of 2 and p of 3 and p of 4, because the domain consists of integers 1, 2, 3, and 4. Okay, because p of 4, which is a statement, this is, it must be 4 squared. Okay, okay, less than, okay, let me correct first. 4 squared less than 10 is false. Then it follows that for all x p of x is false. Okay, so let's move to existential quantifier. Many mathematical statements assert that there is an element with a certain property. Such statements are expressed using existential quantification. With existential quantification, we form a proposition that uh, is true if and only if p of x is true for at least one value of x in the domain. So let's have this definition. The existential quantification of p of x is the proposition there exists an element x in the domain such that p of x. We use the notion, this notion, okay, for the existential quantification of p of x. This symbol is called existential quantifier. So this notion can be read as there exists x p of x. Okay. So the domain must always be specified when a statement there exists x p of x is used. Furthermore, the meaning of there exists x p of x changes when the domain changes. Without specifying the domain, the statement there exists x p of x has no meaning. Besides the phrase there exists, we can also express existential quantification in many other ways, such as by using the words for some, or for at least one, or there is. The existential quantification there exists x p of x is read as, okay, there exists x such that p of x, or there is at least one x such that p of x, or for some x p of x. Meaning the existential quantifier, okay, can be summarized using this table. So in this case, we have this symbol. So this can be read as there is an x such that p of x. Okay, when true, there is an x for which p of x is true. When false, p of x is false for every x. Okay. So let's have this example. Let p of x denote that the statement x is greater than 3. What is the truth value of the quantification there exists x such that p of x, where the domain consists of all real numbers? So in this case, we can have, because f because x greater than 3 is sometimes true. For instance, when x is greater than 4, the existential quantification of p of x, where there which is there exists x such that p of x is true. Okay, so observe that the statement there exists x such that p of x is false if and only if there is no element x in the domain for which p of x is true. That is, there exists x such that p of x is false if and only if p of x is false for every element of the domain. Okay, so let's have this example. Let q of x denote the statement x is equal to x plus 1, What is the truth value of the quantification there exists x such that q of x where the domain consists of all real numbers? So because q of x is false for every real number x, the existential quantification of q of x, which is there exists x such as q of x is false. Okay. So generally, implicit rather, an implicit assumption is made that all domains of discourse for quantifiers are non-empty. If the domain is empty, then there exists x such that q of x is false whenever q of x is a propositional function, because when the domain is empty, there can be no element x in the domain for which the q of x is true. When all elements in the domain can be listed, let's say x sub 1, x sub 2 up to x sub n, the existential quantification there exists x such that p of x is the same as the disjunction. Let's have p of x sub 1 or p of x sub 2 or so on, or p of x sub n. Okay, because this disjunction is true if and only if at least one of the p of x, p of x of 1, p of x sub 2, and so on up to px sub n is true. Okay, let's have this example. Let q of x denote the statement x equals x plus 1. What is the truth value of the quantification there exists x q of x where the domain consists of all real numbers? I believe that question is already answered. So let's have this one. What is the truth value of there exists x such that p of x, where p of x is the statement x squared greater than 10, and the universe of the discourse or universe of discourse consists of positive integers not exceeding 4. So for the solution, because the domain is the set of 1, 2, 3, and 4, the proposition there exists x such that p of x is the same as the disjunction p of 1 or p of 2 or p of 3 or p of 4. Because p of 4, which the statement 4 squared, that's not 42, that's 4 squared, greater than 10, is true, it follows that there exists x such that p of x is true. Let me correct it first. So there exists x such that p of x is true because 4 squared is greater than 10. Okay. Um, it is sometimes helpful to think in terms of looping and searching when determining the truth value of a quantification. Suppose that there are n objects in the domain for the variable x. To determine whether for all x p of x is true, we can loop through all n values for x to see whether p of x is always true. If we encounter a value x for which p of x is false, then we have shown that for all x, p of x is false. Otherwise, uh, for all x, p of x is true. To see whether there exists x such that p of x is true, we loop through the n values of x, searching for a value for which p of x is true. If we find one, then there exists x such that p of x is true. If we never find such an x, then we have determined that there exists x such that p of x is false. Note that this searching procedure does not apply if there is or there are infinitely many values in the domain. However, it is still a useful way of thinking about the truth value or truth values of quantification. Okay, so let's have Uniqueness Quantifier. We have now introduced universal and existential quantifiers. These are the most important quantifiers in mathematics. However, there is no limitation of numbers of different quantifiers we can define, such as there are exactly two, there are no more than three, there are at least 100, and so on. Of these other quantifiers, the one that is most often seen is the uniqueness quantifier, denoted by uh, this symbol or this symbol one. The notion, this one, this symbol or this one states there exists a unique x such that p of x is true. So this one can be read as there exists a unique x rather, such that p of x is true. The other phrases for uniqueness quantification include there is exactly one and there is one and only one. Okay, that's very clever. So there is one and only one. For instance, you could have there exists a unique x such that x minus 1 equals 0, where the obtain when the domain is at least is a set of real numbers, states that there is a unique real number x such that x minus 1 equals 0. Okay, so this is a true statement. Okay, as x equals 1 is the unique number such that x minus 1 equals 0. So observe that we can use quantifiers and propositional logic to express uniqueness. So the uniqueness quantifier can be avoided. Generally, it is best to stick with existential and universal quantifiers so that rules of inference for these quantifiers can be used. Okay, so let's have quantifiers with restricted domains. So an abbreviated notion is often used to restrict the domain of a quantifier. In this notion, a condition variable must satisfy uh, is included after the quantifier. This is illustrated in the next example. We will also describe other forms of this notion involving the set membership in the other section. Okay, so this one. So let's have this example. Uh, what do the statement for all x less than 0 of x squared greater than 0, for all y not equal to 0 of y cubed not equal to 0, and there exists z greater than 0 such as z squared equals 2, mean, where the domain of each case consists of all real numbers. So in this case, the statement, okay, let's have this one. Okay, the statement uh, for all x less than 0 of x squared greater than 0 states that for every real number x with x less than 0, x squared greater than 0. That is, it states the square of a negative real number is positive. This means that this statement is the same as, okay, uh, for all, okay, x of x greater than 0 implies x squared greater than 0. Okay, so that's the answer. Okay, and then the statement uh, for all y uh, not equal to 0 of y cubed not equal to 0 states that for every real number y with y not equal to 0, we have the statement that is equivalent to for all y, okay, of y not equal to 0 implies y cubed not equal to 0. Okay, and finally, the statement, okay, there exists z greater than 0 such that z squared is equal to 2. Okay, states that there exists a real number z with z greater than 0 such that z squared is equal to 2. Okay, that is, it states there is a positive square root of 2. So this statement is equivalent to there exists, okay, z such that z is greater than 0 and z squared is equal to 2. Okay. So, note that the restriction of the universal quantification is the same as the universal quantification of a conditional statement. For instance, for all x less than 0 of x squared greater than 0 is another way of expressing there exists x such that x less than 0 implies x squared greater than 0. On the other hand, the restriction of the existential quantification is the same as the existential quantification of conjoint of e conjunction rather. Okay, for instance, there exists z greater than 0 such that z squared equals 2 is another way of expressing there exists z such that z is greater than 0 and uh, z squared equals 2. Okay, so let's proceed to the next. So let's have the precedence of quantifiers. The quantifiers there exist and for all, no, okay, I interchange. For all and there exist have the higher precedence than all logical operators from propositional calculus. For example, there exists x, p of x, or q of x is a disjunction of there exists not there exists for all x p of x and q of x. In other words, it means um, for all x p of x or q of x rather than for all x p of x or q of x. Okay, so let's have binding variables. When a quantifier is used on the variable x, we say that this occurrence of the variable is bound. An occurrence of the variable that is not bound by a quantifier or set equal to a particular value is said to be free. Okay. All the variables that occurs in the propositional function must be bound or set equal to a particular value to turn it into a proposition. This can be done by using a combination of universal quantifiers, existential quantifiers, and value assignment. Okay. So, the part of logical expression to which a quantifier is applied is called scope. Okay, for of this quantifier. Okay, consequently, a variable is free if it is outside the scope of all quantifiers in the formula that specify this variable. Okay, so let's have logical equivalence involving quantifiers. In the previous discussion, we introduced the notion of logical equivalence of compound proposition. We can extend this notion to expressions involving predicates and quantifiers. So let's have this definition. The statements involving predicates and quantifiers are logically equivalent if and only if they have the same truth value no matter which predicates are substituted into these statements and which domains of discourse is used for the variables in the propositional functions. We use the notion, this symbol, okay, this symbol to indicate that the two statements S and T involved in predicates and quantifiers are logically equivalent. Okay, so let's have this example. Okay, show that there for all x for all x of p of x uh, or q of x, and for all x p of x or uh, or that's not or, that must be and. So let's read it again. Show that uh, for all x of the quantity p of x and q of x, and for all x p of x and for all x q of x are logically equivalent where the same domain is used throughout. Okay. Um, this logical equivalence shows that we can distribute a universal quantifier over a conjunction. Furthermore, we can also distribute an existential quantifier over a disjunction. However, we cannot distribute a universal quantifier over a disjunction, nor can we distribute an existential quantifier over a conjunction. So for the solution, to show that these statements are logically equivalent, we must show that they always take the same truth value no matter what the predicates P and Q are, and no matter which domain of discourse is used. So suppose that the particular predicates P and Q with a common domain. We can show that okay. So we can show that for all x, uh, the quantity P of x and Q of x, okay, and we have for all x P of x and for all x Q of x, okay, are logically equivalent by doing two things. First, we show that if we have to show that um, you have for all x of p of x and q of x is true. Okay, if this is true, then uh, we could have uh, for all uh, for all x p of x and for all x q of x is true. Okay. Second, we need to show that if for all x of p of x, rather, it must be p of x, and for all x of q of x is true, uh, then uh, for all x of p of x and q of x is true. Okay. So suppose that we have suppose uh, that for all x of p of x and q of x is true, this means that um, if a okay if a okay is in the domain, okay, is element of the domain, then you could have p of a and q of a is true. Hence, we have p of a and you have q of a is true. Okay, because p of a is true and q of a is true for every element in the domain, we can conclude that for all for all x p of x and for all x q of x are both true. Okay, so this means that for all x p of x and for all x q of x is true. Next, suppose that suppose that uh, for all x p of x and for all x q of x is true, it follows that uh, it follows that for all x p of x okay is true and for all x p of q not p of q, it must be q of x. You have uh, q of x is true. Hence, if a is a domain, okay, so we could say that if a is an element of x or domain, okay, then we could have the p of a is true and q of a is true. Okay, because p of x and q of x are both true of all elements in the domain, there is no conflict using the same value of a and b here. Okay, a rather here. It follows that for all a, p of a and q of a is true. So it follows that for all x of p of x and q of x is true. Oops. We can now conclude, okay, that the two statements are equivalent. Okay, so let's have negating quantified expressions. We will often want to consider the negation of a quantified expression. For instance, consider the negation of the statement, every student in your class has taken a course in calculus. So this statement is a universal quantification. Namely, you have for all x, p of x, where p of x is the statement X has taken a course in calculus, and the domain consists of the students in your class. The negation of this statement is it is not the case that every student in your class has taken a course in calculus. So this is equivalent to there is a student in your class who has not taken a course in calculus. And this is simply an existential quantification of the negation of the original propositional function. Okay, so namely, we could have there exist x. Okay, okay, so this involved. So this example illustrate the logical equivalence. So this is just the same with the negation of there exists x of p of x, okay, which is equivalent to there exists x negation of p of x. Okay, so to show that there's negation, okay, the negation of for all x p of x, and there exists x p, there exists x such that p of x are logically equivalent no matter what the propositional function p of x and what the domain is. First, note that there exists no note that the negation of for all x p of x is true if and only if for all x p of x is false. So next, note that uh, for all x p of x is false if and only if there is an element x in the domain for which p of x is false. So this holds if and only if there is an element x in the domain for which the negation of p of x is true. Finally, note that there is an element x in the domain for which the negation of p of x is true if and only if there exists x negation of p of x is true. Putting these steps together, we can conclude that the negation of for all x p of x is true if and only if there exists x negation of p of x is true. So it follows that the negation of there exists x p of x and uh, wrong. It follows that the negation of for all x p of x and there exists x negation of p of x are logically equivalent. Okay, so we have this table. So we call this De Morgan's law of quantifiers. The notion, okay, the negation of there exists x p of x. The equivalent statement of this one is for all x negation of p of x. When is negation true, for every x, p of x is false. When false, there is an x for which p of x is true. Another, we have uh, the negation of for all x p of x. This is equivalent, or the equivalent statement would be for all there exists x negation of p of x. There is an x for which p of x is false is when the negation is false or true rather. When false, the p of x is true for every x. Okay, so let's have this example. What are the negation of the statement there is an honest politician and for all Americans eat cheeseburger? Okay, for our solution, okay, we let okay let you have h of x denote, okay, let's say denote um, x is honest. Okay, then the statement there is an honest politician is represented by, okay, So there's honest politician can be represented by um, this symbol x h of x. Okay, so the negation of for all the negation of there exists x as such that h of x, where the domain consists of all politicians. So in this case, the domain are all politicians. Okay, or politicians. The negation of this statement is there. The negation of there exists x such that h of x. Okay, which is equivalent to this is just equivalent to okay this is equivalent to for all x negation of h of x. Okay, so this negation can be expressed as every politician is dishonest. So, okay, so there is an honest politician. So the negation of this one is every politician is dishonest. Okay. Note in English, the statement all politicians are not honest is ambiguous. So all politicians are not honest. Let me check. Let me reiterate that this is ambiguous. The common usage, this statement often means not all politicians are honest. So consequently, we do not use the statement to express this negation. That's why we have every politician is dishonest. Okay. For the second, all Americans eat cheeseburger. So okay, we let let's say C of X, okay, denote, okay, X eats a cheeseburger, cheeseburgers. Okay. So then the statement all Americans eat cheeseburgers is represented by, so this can be represented by the negation of for all x c of x. Okay. Where the domain consists, okay, so here the domain consists uh, consists of all Americans. Americans. The negation of this statement is so the negation of this statement would be the negation, okay, the negation of uh, for all x c of x, okay, which is equivalent to, okay, which is equivalent to there exists x negation of c of x. Okay. This negation can be expressed in several different ways, including some Americans uh, do not eat cheeseburger. Okay. So let's have some Americans does not eat cheeseburger, and there is an American who does not eat cheeseburgers. Okay. So the answer for the second statement, okay, it could be some Americans does not eat cheeseburger and there is an American who does not eat cheeseburgers. So let's have another example. What are the negations of the statement um, for all x of x squared greater than x, and there exists x such that x squared equals 2? So for the solution, the negation of for all x, such as for all x of x squared greater than x, is the statement the negation of for all x of x squared greater than x, which is equivalent to there exists x such that the negation of x squared greater than x. This can be rewritten as uh, there exists x such that x squared is less than or equal to x. So the negation of uh, there exists x such that x squared equals 2 is the statement the negation of x squared, the negation of uh, there exists x such that x squared equals 2, which is equivalent to for all x, negation of x squared equals 2. This can be rewritten as uh, there exists x of x squared equals 2. The truth values of this statement depends on the domain. So we use the De Morgan's law of quantifiers in in the next example. Let's have this one. So show that the negation for all x of p of x implies q of x, and there exists x for all p of x, and negation of q of x are logically equivalent. So, so by De Morgan's law, all universal quantifiers, we know that the negation of for all x p of x implies q of x, and there exists x such that the negation of p of x implies q of x are logically equivalent. By the fifth logical equivalence, we know that the negation of the quantity p of x implies q of x, and p of x and negation of q of x are logically equivalent for every x, because we can substitute one logically equivalent expression for another in a logical equivalence. It follows that the negation of for all x, p of x implies q of x, and there exists x such that p of x and negation of q of x are logically equivalent. Okay, so that's all for my presentation.